Hello everybody and welcome to today's lesson on triangle inequalities. Our objectives today are we will be able to order side lengths of a triangle given angle measures and order angle measures given side lengths. Also, we will be able to determine whether a triangle can be formed given three segment lengths and determine the range for a possible third side length given two side lengths. Let's take a peek at our favorite website, or maybe one of our favorite websites, www.mathopenref.com, at the relationship of sides to interior angles in a triangle. And what I'm showing you right here is a triangle, and we're going to look at the angles and the sides. If you look at that side, the segment AC here to the right, this is the smallest side, and that is across from the smallest angle. Let's work around this a little bit. We still see that the angle is the smallest. Actually, now that changes, and now we see that angle C is the smallest, and that angle is now across the other side. Moving this around, you see that it changes. If we make the triangle more and more obtuse, the angle B gets smaller, and the side across from it is still the smallest side. Let's switch over and look at the largest. In that triangle, we now have the angle A with 119 degrees is the largest angle, and that's across from the side BC. And as we move things around, so far it's still the same, but as angle A no longer is the largest, B is now the largest, then the largest side of the triangle becomes the side that's across from that. You can keep doing this and also move the triangle in any direction that you want, and the same relationship will still be true. So then let's go back and take note of this. Across from the smallest angle and in our example here, that's angle A. Is the smallest side. Across from the smallest angle is the smallest side, and this side has the name Y, or you could also call it by the segment, which is the segment CB. So across from the smallest angle is the smallest side. Now let's look at our largest angle, and you can see that the largest angle in this example is angle B, and across from angle B is also the largest side of this triangle. Across from the largest angle, angle B, is the largest side, and that is the side that we call Z, or segment AC. Alright, let's look at an example. Order the angles from smallest to largest. So this knowledge that we just discovered about the smallest angle being across from the smallest side and the largest angle being across from the largest side is something that we can use very well to figure out information that we don't have. If we look at this triangle FUN, we do not know what the angle measures are of the three angles, but we can, and we are supposed to, order them from smallest to largest, and all we have at this point is, or are, the side lengths. Well, what is our smallest side length? Clearly 10 is the smallest, and therefore we know that the angle across from it has to be the smallest angle. Angle N is the smallest angle. And what is the next largest side, next smallest, side, would be side with the length of 13, which is across from angle F. And the largest side is the side with the length of 14, and that's across from the angle U. And that's all that we have to do here. And clearly, we can also do the same thing in the opposite way. In this next example, you're supposed to order the sides of the triangle from longest to shortest. So I'm going to have you stop the video here and try this out yourselves, and then compare your work with my solution. Here we go. Hopefully you came up with the same result. The largest angle is angle A with 75 degrees, which is across from segment MT. That makes that the longest. The next largest angle is angle T with 59 degrees across from segment MA. And the smallest angle is angle M with 46 degrees across from segment AT, which makes that segment the shortest. Now, having examined how the angles and the sides of a triangle work together, let's take a minute and think about how can we create a triangle in the first place. Well, we obviously need three sides, but can we use any three sides that we want? We cannot. Let's look at this, for example. Let's look at this attempt at a triangle here that we want to put together with the three sides A, B, and C. It's not complete. Somehow we would have to join these two segments. Let's try that out. Let's move them closer. And as we do that and get closer and closer, we realize they don't reach each other. They're not long enough to actually complete the triangle. In other words, not any three sides can make up a triangle. We have to be careful with respect to the lengths of our three sides so they actually are able to create a triangle. Let's look at this picture here at another triangle, and the length of the three sides are marked on the side, and you see that two lengths, AC and BC, are added up together to give us 41.2 units. And if you compare that to the length of AB, which in this example is 30, that is clearly greater than 41.2 is clearly greater than 30. Now again, we can move things around. We can change the triangle, make those two sides smaller and smaller and smaller. And as you see, we can make it as small as we want, but in order for this to still look like a triangle, the two sides added up together, the smallest we can get is 30.2, and that's still larger than 30. We can make it bigger again, of course, too. And the same is true if we move the triangle around from another vertex. The two sides, or any two sides really, added together always have to be more and longer than the third side. And this actually leads us, and as you can see on this page already, to the triangle inequality theorem. Two sides of a triangle, in this example, segments AB and BC, always have to be larger than the third side, in this example AC, And it doesn't really matter which one. Any two sides together have to be larger than the remaining third side. In other words, the remaining third side always has to be smaller than the sum of the two other sides. Now, what is the smallest that the third side could possibly be? Let's look back at our example and let's think about it for a little bit. AB in this example is the third side that we're looking at, and it has to be less than the sum of those two, but what can be the smallest? If we draw this triangle further here, all the way to the side, then you can see that the third side AB always has to be at least a little bit more than the distance, in other words, the difference between the two sides that I'm moving around. Otherwise, we would not be able to connect the three vertices. So the triangle inequality theorem states that given two sides of a triangle, the third side, and in our example this third side is segment AC, has to be less than the sum of the other two sides. In other words, the sides AB plus BC, but it also has to be greater than the difference of the other two sides. In other words, AB minus BC. Circle, highlight the words difference and sum, because that is really what it comes down to. The third side of a triangle always has to be more than the difference of the other two sides and less than the sum of the other two sides. Here goes an example to try this out. Can the following lengths make a triangle? Example 3, we got 6, 10, and 15. Well, let's try it out. 10 plus 6 is 16. 10 minus 6 is 4. And clearly, a third side 15 is greater than 4 and less than 16. So our answer is yes. Let's look at example 4. 6 plus 10 is equal to 16. So since we took the two smaller sides and added them together, we don't even have to do the difference, because we know that the larger side will always be more than the difference of the two of them. But in this case, it's also more than the sum. In other words, if you made a little picture, you would realize that one side is 17, the other 6, and the other 10. They will not be able to join and form a triangle. Therefore, the answer is no. These three sides cannot make a triangle. And let's look at our last example. 6 plus 10 is equal to 16. Again, we don't have to do the difference. 16 is definitely going to be more than the difference of those two numbers. But looking at the sum of them and realizing that if we have side 16 here, the two other sides, 6 and 10, would just be able to touch each other and would be exactly on the line 16. In other words, this combination of sides also cannot make a triangle. We can also use the triangle inequality theorem to determine a possible range of lengths for the third sides. If we don't have that yet, if we have the other two sides given. As in this example, we have two sides, one of them has the length of 6, the other one the length of 10, and we are supposed to determine what numbers could x be. 10 plus 6 is equal to 16. 10 minus 6 is equal to 4. In other words, the third side, which we also call x, must be larger than 4, but smaller than 16. And that same thing we could also write saying it must be between 4 and 16. All right, so far so good. Now go ahead and watch the second part of this tutorial.